Section 6.6 is going to talk about a normal approximation to a binomial random variable. And let's first try and understand why we need to make such an approximation. So the normal curve is going to be used to approximate a binomial probability. Let's understand it from the point of view of problem number 19, which hopefully we'll do in a little bit. You've got 1,002 people in this survey, and 701 of them said they voted in a recent presidential election, although voting records show that only 61% of eligible voters actually showed up. So, wow. Seemed like we got a pretty good number of people who said they voted, even though only 61% said that they did. You would expect something around, 610, maybe 612 people, given this percentage, as opposed to the 701 said, yeah, I voted. Now, to actually calculate that probability that you get at least 701 that actually did vote, you'd have to find the probability that 701 voted, plus the probability that 702 voted, plus the probability that 703, 4, 5, 6, all the way up to 1,002. That could take a while. That would kind of ruin your weekend if you had to do that by hand. Even doing it on Google Sheets would be kind of a little bit of a pain. So what we're going to do is try and get at that probability through a different means. And to that end, let me share with you a little visual. And I think what inspired this is a former colleague of mine who's since retired. But his mother was one of 22 children, which is like staggering. Wow. Did you put name tags on them after a while? I mean, seriously, that's just a crazy number of kids. The probability of, any number of girls amongst those 22 children is shown here. Now, what does this histogram looking figure look like? What is it reminiscent of? What shape? A bell curve, right? And that's kind of the basis of our work in this section, is that a lot of times these binomial probabilities can be approximated with a bell curve. So let's understand under what circumstances we can do that approximation, and then we'll practice 3 or 4 problems depending on how many you want. So, all right, so under what circumstances can you make this approximation? Well, the first thing you have to do is you have to make sure that it fits. So let me write down a few things. Conditions under which a normal approximation to a binomial random variable can be made, or to a binomial probability can be made. Well, the first thing that has to be true is it has to fit. And I hope you remember that acronym. It was a fixed number of trials. What was the I part for? Independence. T was 2 outcomes. And then same probability of success throughout the trial. So it has to fit. Secondly, the curve that you're going to use, the normal curve, has to be a good enough fit to approximate these probabilities. And that's going to mean that n times p has to be greater than or equal to 5, and n times q also has to be greater than or equal to 5. So n times p, that's your expected value. That's the mean of this distribution. It's how many you expect. How many successes do you expect? At least 5. N times q, now remind me, what's q equal to? 1 minus p. So if this is the number of expected successes, this is the number of expected failures. So the number of expected successes and failures both have to be at least 5 in order for this approximation to work. So next, we're going to use this curve, use n, which is distributed normally with a mean equal to n times p, and a standard deviation equal to n times p times q. Basically the mean and standard deviation of the corresponding binomial random variable. And last but not least, in doing these approximations, you need to make a continuity correction. Make a continuity correction. What is that and why are we doing it? Well, there's a big difference between a binomial random variable and a normal random variable. A normal random variable is a continuous variable, like IQ or height. They can take on, all kinds of different values. But with a binomial random variable, you're kind of stuck. You can't have 3.4 girls. It's either 3 or 4. You can't have these values in between. And when you try and use something which is continuous to approximate something which is discrete, you kind of run into that little problem that one of them is continuous and one of them is not. So what we're going to do is we're going to make a continuity correction. We're going to correct for that. And that's what this handout's about, is just to practice the idea of the correction. So the idea on making this correction is you're going to make your areas underneath the curve bigger by 1/2 on each side, if possible. So for our first one, suppose you're looking at a normal curve and you're trying to find the area between, say, 20 and 60. And this is going to reflect some binomial probability. Before you make your area calculation, you need to make this area bigger by 1/2 on either side. So over here to the left, make it a little bit bigger, and over here on the right, I'm also going to make it a little bit bigger. So instead of using numbers of 20 and 60, I'd use numbers of 19.5 and 60.5. You're making that area bigger to allow for the fact that you're approximating something discrete with something continuous. Now, just to do something a little bit more different than what we just did, let's get rid of the 60 here and make that, say, an 80. So suppose in this next one that I'm trying to find the probability that x is less than 80. And I'll make it less than or equal to 80. Not that it matters for the continuous distribution. So that puts an 80 here. And kind of like the last one, I need to make the area bigger by 1/2 on, either side. So that's okay on the right-hand side. So just draw in a little extra area here. If I make it bigger by 1/2 on the right-hand side, then that's going to be 80.5. But can I make it bigger on the left-hand side? Well, this area goes down to -infinity. You can't really get to the left of -infinity. So that's it. You're really only going to make it bigger on one side. If you wanted to find this probability that x is less than 80, to approximate a binomial random variable, you'd really be looking up 80.5 when you went to the normal tables or Google Sheets or whatever. Why don't you try this one down here? So this is the probability that x is greater than 35, so I got a 35 here. What would you actually have to do in order to find a corresponding probability using this curve? what would you be looking up? Well, if you made it bigger by 1/2, what number is going to be there? 34.5. Okay, so again, it's just making it bigger by 1/2. 34.5. Okay, last one like this. We're right here at x equal 25. It's not less than 25, it's not greater than 25, it's actually equal to 25. Now for the normal curve, you're going to run into a problem because there's no area underneath 1 point. There's just 0. Nothing. But if we're using this as an approximation, then kind of like these other ones, I got to make the area bigger by 1/2 on both sides. So that'd be 1/2 on the left, so here, and then 1/2 on the right, so here. But it's on both sides. So do it on both sides. Nick, what would I look up? Instead of 25, what number should I use here now? Good. 24.5 and 25.5. So that's what's going to give you your area underneath this normal curve, and then you can use that to approximate a binomial random variable. Yay. Now that binomial random variable is going to be approximated by a normal curve with this mean and this standard deviation. You could also write that as square root of n times p times q. Let's start with problem number 6. Okay, so in problem number 6, we're talking about the number of, where is it? I think it's boys out of 8 births. Let's just double check. Yeah, number of boys out of 8 births. Now, instead of using kind of the loosely assumed 0.5, I think they use a more nationally accurate 0.512. We can check that this fits. You got a fixed number of trials, which is 8. They're independent. You know, what happens with one couple's child is going to be independent of what happens with the other. 2 outcomes, boy and a girl. Same probability. We kind of get that through the problem, and if you wanted to be really fussy about it, the 5% rule. But that part is okay. The next part, we need to figure out NP and NQ, or 8 times 0.512 and 8 times 0.488. So 8 times 0.512, I think, is 4.9096, right? 4.996. We good there? Is that right? Did someone check me on my math? All right. It's got to be pretty close, if not exactly right. So, but there's one problem here. Does anyone see the one problem with this? These numbers have to be greater than 5, and that's less than 5. So we can't do a normal approximation in this case. So the normal approximation should not be used. Bummer. I was so looking forward to trying that. Okay, see you next week. All right, just kidding. Let's try a different one. Problem number 8. So at this point, you'd actually have to calculate the binomial random variable itself or something else, but you shouldn't be doing the methods outlined in this section. It's not something for which you're going to get a good approximation. Problem number 8, you're going to guess on a standardized test. So there's 50 questions on this test. There's 5 questions or 5 possible answers, and one of them is right, so you got a 20% chance of guessing right. We want to find the probability of exactly 12 correct answers. Before we get to that probability and its calculation, let's see about whether or not this fits. Does it have a fixed number of trials? Yeah. If you guess on problem number 10 right, is that going to help you guess on problem number 11 right? Or are they independent? Independent. Yeah, guessing is just guessing. They're going to be independent. 2 outcomes, you got it right or you got it wrong, and you got a 1 in 5 chance throughout the test of guessing right. So, nailed it. This is definitely a binomial random variable. If we're going to do a normal approximation, we've got to check something else. We've got to check n times p is greater than 5 and n times q is greater than or equal to 5. So 50 times 0.2 is 10, and 50 times 0.8 is 40. Let's try and understand these things a little bit more. This is your number of expected successes. This is your number of expected failures. You expect to get about 10 right and 40 wrong. That's what you're expecting. In order to do a normal approximation to the binomial random variable, you want to make sure that the number of expected successes and failures are both at least 5. And we have that. We're in good shape. So let's move to the next part then. Let's actually find an approximation to the probability that x equals 12. What's the probability that you get exactly 12 right? Now, there's nothing really wrong with calculating that binomial probability directly from our binomial PDF, but let's practice what we're trying to in this section. We need a couple things here. So this is still problem number 8. I need the mean, which is n times p. I've already got that. I have a mean of 12. And a standard deviation equal n times p times q, which is 50 times 0.2 times 0.8. So it's going to be the square root of 8. Yeah, square root of 8. Is that right? Yeah, square root of 8, about 2.828. So this is the normal curve that we're going to use to make our approximation. Let's take advantage of a couple of the blank curves that we have down at the bottom here. Let's write in that this normal curve is distributed with a mean of 10 and a standard deviation of 2.828. Connor, what should I label this line with down here? 10. Yeah, 10. And we're trying to find the probability that x equals 12, which is out here. 12. Now I can't just look up the area underneath the point 12 in the normal tables here because there's not going to be any area. There's no area underneath the point. What do I have to do before I find this probability, or I approximate this probability? Anyone know? Yeah, you got to add that continuity correction. So I'll put an area of 1/2 on one side and 1/2 on the other side. So both of these get bigger by 1/2. It's amazing. Even though this one looks twice as thick as the other one, they're both 1/2. So that's 12.5 and that's 11.5. So that's the area we need to look up underneath this particular normal curve. You can do that on Google Sheets. You can do it on your graphing calculator. You can do it on StatDisk. To do it on StatDisk, you'd first have to calculate the z-score. Remember, z equals x minus mu over sigma. If you calculate a couple z-scores, StatDisk will give you the area corresponding to those z-scores. On a graphing calculator, that's going to be the easiest on a graphing calculator. It's going to be norm CDF of the lower, which is 11.5, and then the upper, which is 12.5, and then the mean, which is 10, and standard deviation of 2.828. So that's going to be the easiest one. On Google Sheets, it's a little bit more challenging. Google Sheets is going to give you the area to the left of a particular point on the normal distribution. So in Google Sheets, you're going to have to look up two areas, to the left of 12.5 and to the left of 11.5. What do you have to do once you find those two areas? The left of 12.5 and the left of 11.5. So, yeah, subtract them. So for graphing calculator, 11.5, 12.5, mean of 10, and a standard deviation of 2.828. So I'm getting about 10.957 or 0.10957. Let's take a quick peek at it in Google Sheets. So let's see. I'll just clear these out. So equals norm distribution. Let's see. Distribution of, let's see, we'll start out with 12.5, comma, 10, comma, 2.828, comma, true. Actually, it should be 828, comma, true. Something doesn't look right. Oh, I guess all right. And then equals same thing, norm distribution of 11.5, comma 10, comma 2.828, and true. It's the difference between these that makes it, that represents our final answer. So equals, click this one minus this one. So I'm getting exactly the same answer either way. Whatever you find most convenient, use that. Okay, how are we with this first one here? Pretty good? All right, some nods there. That's good. It's appreciated. We're going to try a couple more. By the end of this, you should be comfortable with doing this. If you're not, please raise a hand, ask some questions, get some help. Let's turn our attention back to what started this one, which would be problem number 19, all the voters. How likely is it that we're going to get so many people who said, yeah, oh yeah, I voted, when actually only 61% of the people did vote? Let's take a look at that one. So you had 1,002 people were surveyed. 701 of them said that they actually voted. But voting records show that 61% voted. So what's the probability if 61% of them voted that just by luck you got 701 of them in your poll that actually did vote? What's the chance of that? Is it going to be pretty high, you think? We'll find out. Okay, so some relevant statistics that we need to do this problem. This is number 19. We've got an n equals 1,002. Probability of success is 0.61. Let's check out a couple things here. First of all, does this fit? Fixed number, okay. Independent, you know, what random people do with their voting is going to be independent. Two outcomes, they voted or didn't. Same probability, kind of. You get that through the 5% rule, so we're okay there. There's one other thing I got to check, that's NP, which is going to be 1,002 times 0.61, or 611.22. And that's clearly greater than or equal to 5. Lauren, what's Q going to equal for us? Thank you. 0.39 times 1,002 is 390.78. And again, that's greater than or equal to 5. So we're in good shape. We can make a normal approximation to this binomial probability. And this is really a much better one to do it for. Because without this kind of approximation, you'd have to calculate these probabilities for 701, 702, 703, all the way up to 1,000, and then add them all up. Now, it's not too hard with technology, but let's practice this. Certainly, it's easier than it used to be. So x is going to be normally distributed with a mean of 611.22. We need the standard deviation. So the standard deviation is going to be the square root of 1,002 times 0.61 times 0.39. Typically speaking, what I'll do is this, 1,002 times 0.61 times 0.39. But the one thing that I need here that I don't have yet is the square root. So my shortcut is to raise that to the 0.5 power. Fancy way of getting the square root. So I'll just take the square root of your previous answer. And that's about 15.44. That's good enough. So I want to work with a distribution with a mean of 611.22 and a standard deviation of 15.44. 15.44. Personally, I think it's a really good idea to label your distributions, to draw it, because it can help you catch mistakes. Charbel, what should I label this vertical line with? Thank you. 611.22. Now I'm trying to find the probability that x is greater than or equal to, what, 701, wasn't it? Let's just double check. Yeah, 701. So 701 is clearly going to be someplace over here. Which way should I shade my curve? To the right or to the left? Do I want the area to the right of 701 or to the left of 701? Let's look back here. It says, find the probability that among 1,002 randomly selected eligible voters that at least 701 voted. So Ryan, Am I going to shade to the right or to the left? So to the left is going to be at least 701. Yeah, other left, right? Good. All right, thank you. Yeah. All right, so we're going to shade to the right here. It's this area. And that's important because that tells me that my area is going to be something much less than 1/2, right? It's kind of out here in the tail. And that can help you with a mistake, especially if you're using Google Sheets. When you look up your numbers in Google Sheets, it's going to give you the area to the left. So for those of you using Google Sheets, you're going to have to take 1 minus that area to get this area in the tail. Now, we're not quite done here. There's one other thing we got to do. Kayla, what else do we got to do before we look up our probabilities? Yeah, perfect. Our continuity correction. So let's squeeze in that 1/2. Thank you so much. So squeeze in that 1/2. What is this new point going to be here then? 700.5. Good. So you want to find the area between 700.5 and infinity. Now, if you're doing this on Google Sheets, it's going to give you the area to the left. So you're going to subtract that from 1. If you're doing it in your graphing calculator, you still got to be a little bit careful because the area or your calculator is going to work with the lower limit, and then the upper limit. What's the upper limit on this area, realistically? 1,002? Yeah, you could use 1,002 or infinity. I mean, either one. I mean, technically the normal curve goes out to infinity. But it's tough to put infinity into your graphing calculator. So what I do is I choose a number that's really, really big. Second distribution, normal CDF. Lower limit is 700.5. Upper limit, let's go 10,000 works. 100,000 is good too. You know, if you want to be more comfortable, that's fine. The mean was 611.22, and the standard deviation was 15.44. Is that a really big number? 3.69? Or is there something else going on in this one? There's this little e -9 here. Yeah, it's scientific notation. So it's really 3.693 times 10 to the -9th. Is that a big number? Is there a good chance that we got at least 701 voters like that? No. Now, if you were to write that in regular decimal notation, 0.00000003693. Wow. What's that saying? Some of our voters are liars. And that's actually kind of a big problem with conducting research, conducting polls. People tell you what they think you want to hear. Oh yeah, I voted, sure. So it's a problem. The other problem, it is a big problem with lying because sometimes you have to ask sensitive questions. One of the ones we'll tackle in section 7.1, hopefully if we get there, maybe not today, but talks about oxycodone. What's that? Part of the opioid crisis that maybe you've heard a little bit about. Kind of going crazy in this country. So, but it's tough to collect good data. We saw that in the last presidential election. Hillary Clinton was supposed to be comfortably ahead right until the end, and all of a sudden, bam. And it's because a lot of those undecided voters broke Donald Trump's way. So the polling was way off in that. All right, we're not worried about that stuff so much. We are worried about being able to calculate these probabilities. How are we looking at problem number 19 there? Okay? All right. On Google Sheets, let's take a look. It So we want the normal distribution. The mean was 611.22. And then standard deviation, or the mean and standard deviation. No, actually, you know what? I don't want that. I want to put in the x value first. So it'll be 700.5, then the mean, then the standard deviation, which was 15.44, comma, true. Now this is going to give you the area in the left tail. We don't want the area in the left tail. We want the area in the right tail. So we can say, all right, well, that's going to equal 1 minus, and then click on this cell, and we're getting pretty much the same thing. Okay? All right. I wonder if I type in something off a little bit. Looks like it's a little bit in disagreement with what we got from the graphic calculator. Okay. Yeah, there's a small difference, but either way, the probability is remarkably small. Somebody in that poll is lying. That's the unmistakable conclusion. Okay, let's try problem number 16. So what you should do in problem number 16 is make sure you're pretty comfortable with this stuff. If need be, we'll do one more, problem number 17. But let's take a look at problem 16 together. Based on a study by Dr. P. Sarita at Indiana University, assume that 12% of us have green eyes. In a study of 650 people, it's found that 86 of them have green eyes. Find the probability of at least 86 people with green eyes amongst 650 randomly selected people. Let's convince ourselves, first of all, that this is actually a binomial random variable, and this probability would be a binomial probability. 650, that's fixed. Independent. If somebody has green eyes, doesn't affect whether or not you have green eyes. Those are independent events. Two outcomes, you do or don't have green eyes. And then, let's see. The last one is the same probability. Yeah, there we can invoke the 5% rule because 650 is certainly less than 5% of the people in this country. So we're okay there. There's one other assumption that I have to check, though. What's that other assumption? So n equals 650, p equals 0.12. What's the other assumption that I have to check? Good. N times p is greater than 5, and n times q is greater than 5. Okay, so n times p is 650 times 0.12. 78? Is that right? Okay. 78, thank you. N times Q is 650 times what? 0.88. And whatever it is, it's certainly going to be greater than 5. Both of these are greater than or equal to 5. So we're okay with those assumptions as well. And what that's saying is that the normal approximation to this probability would actually be pretty good. Wouldn't be that bad. And it'd be much better than having to calculate the probability that x equals 86 plus 87 plus 88 all the way up to 650. That would be a drag. It would certainly ruin your weekend. Let's calculate a few more things. The mean we already got, that's 650 times 0.12 is 78. Standard deviation, square root of 650 times 0.12 times 0.88. Thank you. 8.28. I'll round it off to third digit, 8.285. Thank you. let's draw our curve. Angela, what should I label this middle line with? Perfect, 78. Now the problem is asking us to try and find the probability that x is greater than 86. So that's going to be out here. Kira, is 86, x at least 86, am I going to shade to the right or to the left here? Good, shade to the right. And that tells me something important about my probability. Again, it's an area in the tail. Again, it's going to be something less than a half, probably, a fair amount less than a half, not sure. Depends on the standard deviation. I'm not yet done. Tyler, what else do I need to do before I start calculating probabilities? Good. Need to make this bigger by a half. So let's do that. Oh, no, wait, no, thank you. All right, so 85.5, and we're going to use this mean or this distribution, normally distributed with a mean of 78 and a standard deviation of 8.285. So go through that one and try and calculate that probability. Anyone want to borrow a calculator? How much is left of CF to key after all the hurricanes? I went for it. Did you? For the keys or driver's licenses. Okay. What are you guys getting? What percentage? 18.26 or something like that. All right, that's good. So hopefully everyone's on board with this percentage, about 18.267, somewhere about there. So not terribly high, not terribly low either. So are we okay finding this? Are you able to find it on Google Sheets or whatever your favorite medium is? Okay. There's a follow-up question here, kind of a part B, and that is 86 people with green eyes significantly high? Is that unusual to get that many people with green eyes? I mean, the mean is only 78. That's what you expect on average. Did we get something unusually high? I'll wait you out. Not really. I mean, this can happen almost 1 out of 5 times when you do this, all right? It'd be unusually high if this percentage was less than, say, 0.05. That's going to be kind of our gold standard for something which is unusual, if it has less than a 5% chance of happening. So that's where our cutoff is. And I think I mentioned this before. It goes back to an off-the-cuff remark made by a statistician around the turn of the 20th century named Ronald Fisher. He just said, oh, with about a 1 in 20 chance. Yes? Let's see here. No, the percentage that they asked was at least 86. Yeah, if you're asking for the probability that you get exactly 86, it'd be a different probability. And it'd probably be much less. It would change things. I think we're correct in referencing this probability up here, because when you look at all the things that can happen, there's 651 different possible outcomes. You could have anywhere between 0 and 650 people with green eyes. Now, a lot of these are going to be pretty unusual, but because you're taking that 100% probability and dividing it up over 650 events, most of those probabilities are going to have to be really, really small, necessarily, because you're dividing it up by so much. So to look at any particular event, chances are it's going to be pretty small. So what you do is you look at something which is that much or more extreme. What's the probability of getting at least 86? So 86 or higher, and that gives you a better sense of just how unusual an event like 86 is. So we're going to be sticking with that. And maybe I'll try and revisit this and explain it again some more. But the bottom line is we want to talk about not just one event, but the probability of a whole tail of events. Everything in that right tail. It's a great question, and I hope you bring it up again if we don't run into it by some other means. All right, did you want one more? Should we do one more like this? Make sure you guys got it down pretty good. It's up to you. Going once, twice. Okay, we're going to do one more then. See, should have spoke up. All right, so problem number 17. Hey, the good news, though, is this was one of your homeworks. So you get to do one of your homeworks in class. So it's going back to the experiments with Gregory Mendel. In one sample, you had 920 peas. 705 of them had red flowers. So Mendel assumed that this should happen with about a 3/4 of a probability. So the two relevant numbers that you're going to need here are n is 929 and p is 3/4, 0.75. So give that one a shot, see what you can do with it. Okay, so let's look at this one together. I'm just curious. How many people check the assumptions? First of all, that it fits. Secondly, that NP and NQ were both greater than 5. Yay, well done. Good deal. That is something I'd like to see. Be in a good habit of checking your assumptions. Once that's checked, we already got our mean. That's 696.75. 696.75. Standard deviation, 13.198. We're trying to find the area to the right of 705. That is at least 705. So I'll shade that area to the right. But 705 is not what I want to put in my calculator. I need to do my continuity correction. So that continuity correction gives me 704.5. This is the only place where you're going to do a continuity correction. This is the only time is when you're making a binomial or a normal approximation to a binomial random variable. There's a tendency to people want to do this continuity correction for everything. This is the only place. So, unfortunately, on the test, when you come up to me and say, is this more than what I need to do the continuity correction? I can't answer you. Sorry. You just got to know this is the only section in the entire book. Brian? That was the problem? You wanted to find the probability of at least 705 or more peas with red flowers. So it came right from part A. Is that part. So with our continuity correction, then we're going to type in 704.5. Let's take a look at the command. Using normal CDF on our graphing calculator. The lower limit, 704.5. Upper limit, just pick something really, really big. I picked 10,000. If you want to be really, really sure, pick 100,000. Mean and standard deviation. Should get about 27.85% chance of something like this happening. So, not unusual at all. How are we looking on problem number 17 there? Pretty good, I hope. All right. So let me give you some homework then. For homework, try problems 1 through 17 in both 13th and 12th edition. 13th. I think the 13th edition and the 12th edition might both label this as section 6.6. I'm not sure. But I think, I don't know. In any case, it's normal approximations to binomial random variables.